All right, hi y'all. Today is the fundamental theorem of calculus, truly fundamental to studying calculus. So the FTC is the abbreviation. And while we've learned, the three theorems, the mean, intermediate, and extreme value theorem, those are kind of one set of theorems. And then the fundamental theorem of calculus, we'll have this first form and we'll have the second form. Super important. So basically what the fundamental theorem of calculus is how you do a definite integral by hand. So far we've estimated definite integrals by using Riemann sums and trapezoidal sums. We have calculated definite integrals as long as the shape underneath the curve was like an exact geometry shape that we could calculate using geometry. And today we're finally going to do definite integrals where it's not an exact geometric shape, and we're going to do it from just the calculus algebra point of view. All right. So first thing is to distinguish what the difference is between an indefinite integral and a definite integral. What the answer, what we're expecting, and then like what the answer means. Okay. So this is what we did yesterday, the antiderivatives, right? If I'm integrating 3x squared, I would use backwards power rule, and I know that this was one more power than it was originally, so 2 plus 1 would give me 3, and then I'd multiply by 1/3, so 1/3 of 3 was just 1, and then x cubed plus c, right? So what did we get? We got, an equation, right? So I said we got an equation, and that equation also always contained a plus c, right? Don't forget the plus c. And what this is saying, right, this is really a family of solutions. Right? If our original function was, 3x squared. So if we're talking about, our original function, if our original function was y equals x cubed, right? Plus c. If our derivative is 3x squared. So if we were to graph 3x squared, right? We know it's a cute little parabola, slightly thinner than our parent function, right? And if we were to think about that this is a derivative of this function of x cubed, right? If it's just plain old x cubed, hopefully you remember that x cubed looks like this, right? Increasing till we get to 0, increasing after 0, right? So increasing. That's why you notice that this x squared is above the x-axis the entire time, because this x cubed, right, plus c is constantly increasing. And plus c, hopefully you remember that's just like a vertical shift. If this was like x cubed plus 5, that would shift this up by 5, right? If it was x cubed minus 3, that would shift it down to, -3. So we consider this is called what we call like a family of functions. So all of these x cubed plus c is this idea that no matter which graph we had, all of those would yield that same derivative graph. Okay. So for an indefinite integral, we're just expecting an equation plus c. But a definite integral, we're expecting a value. It's the numerical answer based on like the area underneath the curve. Okay. So one thing, I couldn't get my computer to type this, but the integral from 3x squared, if you're going from 0 to 4, you're going to do the exact same step you did here first. That the antiderivative of 3x squared is x cubed. Okay. So you're going to go x cubed. And then instead of writing plus c, we'll talk about why the plus c you don't need to write if it's a definite integral. You're going to write this straight line, which means evaluated from, and you're going to start here at 0 and go here to 4. So you'll say x cubed, evaluated from 0 to 4. And then notice you plug in the top number, so 4 cubed, minus plugging in the bottom number. Oh no, I typed that in wrong. So 4 cubed minus, this should be 0 to the third. Oops, so 0 to the third. So that would just be 4 cubed, 64. Okay. Oops, didn't notice that. Okay, so what do we expect? We expect to get a number, right? An actual like numerical value. And what is that meaning? That is the area underneath the curve. So if we look at the original problem, right, 3x squared, so if we graphed 3x squared, we'd be calculating from 0 to 4, the area underneath the curve is exactly this value right there. So there was exactly 64, units, square units in between there and there. So here I just wrote the area between the curve and the x-axis. So this is the area, oh gosh, that's not gonna work. Try this one, the area between the curve and the x-axis. And I do put it in quotes because we already know the actual definition of definite integral. That was that whole long limit thing with the n going to infinity where we break it up into n subintervals. But for our brains, you can just think of definite integral as the area underneath the curve. Okay? So that work that we did right there, that is the fundamental theorem of calculus. So where you take the antiderivative, right? And then you're going to evaluate from 0 to 4, and then plug in the top thing minus plugging in the bottom thing. That's what the fundamental theorem of calculus says. So in order to find a definite integral, as long as the function is continuous on the closed interval from a to b, and g is an antiderivative of f of x, then the integral of f of x dx going from a to b will equal g of x evaluated from a to b, right? And then you're going to plug in the top thing minus plugging in the bottom thing. So you're going to plug in b minus plugging in a. Okay? Main thing that students forget on this is to take the actual antiderivative. So, you know, when 3x squared was sitting here, you can't just say this is equal to 3x squared going from 0 to 4. You have to actually think and do the calculus right there. So that will be the part that you got to make sure you're doing. And then let's take a look at this. Now, obviously, if this is in free response, just like all the other things this year, you do not have to simplify your answer. So you could leave it a big mess, right? But if it's in the multiple choice, you'll have to simplify it all the way down. So I think for these, I will simplify it just as if it was free response. And then you can take a look at the answer key to see what the actual final answer would be as if it was multiple choice. Okay. Just so in the video here, we're focusing mostly on the new calculus. You can save the algebra for your brain at home. All right, so here we go. Definite integral from 1 to 3 along negative x squared plus 9 dx. So first step is just to take the antiderivative of each of these terms, right? So negative x squared, I'm thinking about backwards power rule on this. So it was 2. I know I need to add 1 to that. So that's going to become x to the third. And whatever the new exponent is, you reciprocate out in front. So 1/3. And the negative was there, so the negative stays. So negative 1/3 x cubed. Right? The antiderivative of the next term, plus 9, is just a new term. So I can just say plus 9x, right? This is, again, backwards power rule. And since there was no x, it was like x to the 0th, then I can just throw on an x. Right? Because it's my first time and I'm not sure why I don't need the plus c, I'm going to go ahead and write in the plus c. So because we're used to antiderivatives always having a plus c, let's go ahead and include it. Right? And then you're going to say that was the antiderivative. Now you're going to do this new notation of putting this straight line. You're going to say evaluated from 1 to 3. That's telling the reader, me, that you're taking a definite integral. And then the work from here is just to plug that 3 in everywhere you see the x, minus plugging in the 1 everywhere you see the x. So plugging in the 3 minus plugging in the 1. So negative 1/3 stuff cubed plus 9 times stuff plus c, and negative 1/3 stuff cubed plus 9 times stuff plus c. Again, the first one we're going to plug in a 3, and the second one we're going to plug in a 1. So I'm just going to keep going on this first one just so you can actually see what's happening, but on the rest I might stop at that point. Here, obviously 3 cubed, 27, negative 1/3 of that would be negative 9 plus 27 plus c. Right, over here minus 1 cubed 1, so negative 1/3 plus 9 plus c. And now I'll go ahead and distribute that negative. So I'm left with a negative 9 plus 27 plus c plus 1/3 minus 9 minus c. And so what we want to notice here is that every time if you have a definite integral, notice you have a positive c and a negative c. So in fact, you don't need to write it if it's a definite integral, okay? You have to write it if it's an indefinite integral, but they will always cancel if it's for a definite integral. So in fact, I tend not to write them for the definite integral because I don't have to show my work and get to that final, and get to this step where I show that they cross off. So I would normally just not write that at all, okay? So watch out for that. And then if you actually do a little math on this, negative 9, that's negative 18, plus 27, and then plus 1/3. I'm going to cheat here. It looks like we get a final answer of 9 1/3, or 28 thirds. So 9 1/3, which would be the same as 28 thirds. But again, if this is free response, you can just leave your answer right here. As soon as you've gotten this notation off your page and you plugged in the 3 minus plugging in the 1, you'd be good to go. Okay? All right, let's try letter B. Letter B says the integral from 9 to 16 along the square root of x dx. So first thing I'm going to do on this one is just rewrite it so I can see the power. This is really x to the 1/2, right? And so x to the 1/2, again, backwards power rule, stuff to the 1/2. I need to add 1 to that. So that will become x to the 3/2. And then whatever the new exponent is, you get rid of it by having the reciprocal on front. So 2/3. Right? Normally I write plus c if it's an indefinite integral. So I think of indefinite integral plus c. If it's a definite integral, I don't write plus c, but instead I write the straight line evaluated from boom to boom. So evaluated from 9 to 16. Right? Then I'm going to plug in 16 minus plugging in 9. So 2/3, 16 to the 3/2, minus 2/3, 9 to the 3/2. Maybe I'll be consistent, just plug them in red. So 16 and 9. All right, now obviously for your response you can stop, but just because I want to make sure you know how to do these in case they are on the multiple choice, make sure we're comfortable 2/3, 16 to the 3/2, that would be the square root of 16, and then quantity cubed, right? This is 2/3 times square root of 9, and then quantity cubed. All right, so order of operations don't matter on that. You could cube it and then square root it, but without a calculator, this is way easier, right? So square root of 16, 4. 4 cubed, 64. So 2/3 times 64. Minus over here, 2/3, square root of 9, 3 cubed, 27. So it's at 128/3 minus 54/3. 128 minus 54, there it is, 74/3. That makes sense. Again, if this was without, or if this isn't for your response, you could have stopped, boom, right there, second line. All right, let's see how these next two go. So letter C, the integral from 0 to 3 pi over 2 of sine of x dx. And I think I'm just going to move this up just so we have a little space. So the integral of sine, right, antiderivative of sine, is either cosine or negative cosine, right? So that's going to be the struggle. I always memorize that I know my derivatives by heart, right? The derivative of sine is cosine, the derivative of cosine is negative sine. So therefore the integrals are the opposites of that. So I know the integral of sine is negative cosine. So I could say equals negative cosine of x, again, evaluated from 0 to 3 pi over 2. And this is all equal, I just didn't have enough space to write it on the same line. And then plug in the top thing minus plugging in the bottom thing. So negative cosine of 3 pi over 2 minus negative cosine of 0. So the top one goes in first, minus the bottom one goes in. So then cosine of 3 pi over 2, 3 pi over 2 is 270 degrees, right? So that's 0 comma negative 1 cosine sine. So I know that's going to be a 0, so negative 0. And then plus cosine of 0, well that's right here, right? 1 comma 0, so that would be 1. So final answer looks like it's 1. Okay. To connect back to the area underneath the curve, if we look back at the original problem, this was asking us to integrate along sine. So I'm hopeful that you're comfortable that the sine of x looks like this, right? Going up to 1, going down here to negative 1, right? And we were starting at 0 and going all the way to 3 pi over 2. Right? So we were here at 0, and then here would be pi, and so boom, here would be 3 pi over 2. Okay. Notice we got a final answer of 1. The reason we got a final answer of 1 is because it's kind of cool. If I had just integrated from 0 to pi over 2, that's exactly 1. Right? This is also exactly 1. And guess what this is down here, right? This is exactly negative 1. So that positive 1 and that negative 1 canceled out, and that's why we were just left with a positive 1. Okay? So it's kind of fun. Sine and cosine waves, each increment is exactly equal to 1 or negative 1 in those waves. All right, I'm talking too much, sorry y'all. Okay, how about letter D? This says the integral of 1 over x dx, and you're integrating from 1 to e. Okay, so the first thing you might try is rewrite this and go 1 to e, and you're like, oh, that's x to the negative first, dx. And so maybe just on automatic mode, you're like, oh, backwards power rule, I'm gonna add 1 to negative 1. So you try that, and you're like, adding 1 to negative 1 would be x to the 0th, and then 1 over 0, and you might like remember, oh wait, that's not the way I need to go with this, right? This has its own special rule. The integral of 1 over x dx is that natural log, right? The natural log is how we get 1 over x when we derive. So we go natural log, we technically say absolute value of x. And then here we're going to be evaluated from 1 to e. Plug in the top minus plugging in the bottom. So natural log of absolute value of e minus natural log of absolute value of 1. Again, then you'd be consistent, plug in with the red. So e goes here, 1 goes here. Again, perfectly fine to leave your answer like this, but absolute value of e is just e, right? Absolute value of 1 is just 1. Natural log of e is exactly 1, that's one of those values, and then natural log of 1 is exactly 0. So this works out so nicely. Right? To connect back to geographically on this one, geographically, oh my gosh, not geographically, just graphically. If we sketch this 1 over x, right? Hopefully you remember that 1 over x is the hyperbola in the first and third quadrants, and we were evaluating from 1 to e. Isn't that crazy that that space underneath that curve is exactly equal to 1 as well? So that's equal to 1, and this piece right here was also exactly equal to 1. Okay. All right, so that was the front page, the nicest of the problems. Continuing on with example number 2, now we're going to hit some problems where we have to watch out for backwards chain rule. So maybe it's a little much all for one time, but let's check this out. So for letter A, it says the integral from 1 to 13 of the square root, but now it's not just the square root of x, right? It's the square root of 5x minus 1. So this is similar to what we did the second half of the last section. It's like you kind of want to forget about the stuff for a moment. Just pretend it was the square root of something, right? So if you're taking the antiderivative of the square root of something, that's like what we just did on the last page, right? Stuff to the 1/2 will become stuff to the 3/2 with the 2/3 out in front, right? So if I know it's square root of stuff, that was stuff to the 1/2, right? I know the antiderivative of that is going to be stuff to the 3/2 with the 2/3 out in front. You're adding 1 to your exponent. Whatever the new exponent is, you reciprocate. Now I uncover, though, the inside stuff was 5x minus 1. So I know that's going to stay, 5x minus 1. Right? Now, whatever the derivative of the inside is, 5, we need to get rid of that by having a 1/5 out in front. So you're going to multiply by 1/5 out in front. That is chain rule. Okay. And then evaluated from 1 to 13. Okay. Plugging in the 13 minus plugging in the 1. So let's see, that's 2/15. 5 times stuff minus 1 to the 3/2 minus 2/15. 5 times stuff minus 1 to the 3/2. Plugging in 13 and plugging in 1. Right? I'm going to leave that there for now. I'm not going to worry about simplifying that. But you can check my answer here. Maybe I'll throw it up after I do all 4 of these problems. Okay? But that's the calculus involved. Right? That would be great to leave as your final answer for free response. You don't have to keep going. Feel free to pause and try the rest of these, yeah? This one, that 7, is just a multiplier out in front, right? So this is kind of the same. This was 7 times stuff to the -3rd. So imagine if you just had 7x to the -3rd and you were integrating that, right? Well, you would just add 1 to -3. That would become x to the -2. Your new exponent, you would multiply by the reciprocal of that. So the reciprocal of -2 would be -1/2. And the 7 was out in front, right? So it'd be like -7 times 1/2, x to the -2. So it's exactly what's going to happen here. Except it's just not x, it's like stuff. So like 7 stuff to the -3rd is still going to be 7 stuff to the add 1 to -3 becomes -2. Multiplied by the reciprocal of -2, so there's -1/2. Right? Then you finally uncover what the stuff is, and it was 2x minus 1. Right? So now here's chain rule. Because the derivative of the inside was 2, you have to get rid of that 2 with a 1/2 out in front. So, and then evaluated from 1 to 2. So it looks like our final coefficient out in front was -7/4. So -7/4, 2x minus 1 to the -2nd. And so that would be equal to -7/4, 2 times 2 minus 1 to the -2nd, minus -7/4, 2 times 1 minus 1 to the -2nd. Hopefully I'm still in the window. Again, you could just leave that as your final answer. You don't have to simplify. All right, and then C and D on this one, we have cosine of 2x and e to the 4x. So if we have a trig word, right, cosine is stuff. The antiderivative of cosine is going to be regular sine, right? If I know the derivative of cosine was negative sine, then I know this one's going to be positive. So cosine of stuff, right, if it was just x at first, this would have been just sine of stuff. But it's not just x, it's 2x. So because the derivative of 2x is 2, we have to get rid of that with a 1/2 out in front. So 1/2 sine to the 2x, evaluated from -pi to pi. So 1/2 sine of 2 times pi minus 1/2 sine of 2 times -pi. Again, you can just leave your answer like that. I'll show the final answers in one moment. And then this one, e to the. Remember e to the integral and derivative is still going to be e to the. So don't make it harder than it needs to be. And then the exponent is your inside function. So no power rule in these, right? E to the stuff will still be e to the stuff. So it's going to be e to the 4x. But once you uncover that it was 4x, because the derivative of 4x is 4, you need to have a 1/4 out in front. So 1/4 e to the 4x. And then evaluated from 0 to 2. Plug in the 2 minus plugging in the 0. So 1/4 e to the 4 times 2 minus 1/4 e to the 4 times 0. Those would be perfectly great final answers, right? Or you could, if for multiple choice you wanted to keep simplifying, or you had to keep simplifying for multiple choice, you'd want to get down to the final answers, right? Let me show you those real quick. And that would be here. So number 1, it looks like it was, that's ridiculously messy, or letter A, right? It was like 336 over 5, or 67.2. Yeah. This one was 5636, so 28/18, or, oh, it's slightly off the page there. Let's see, 14/9. And then looks like letter C worked out to be 0. And letter D was this 1/4 e to the 8th minus 1/4. Okay. All right. Now let's see few other, these are a little bit less popular style questions, but still fundamental theorem. So just being a little bit more creative. This one says that we can use the FTC if we're given a table or a graph, right? So this one's given a graph. This one, be careful. This one says the integral from 1 to 3 along f prime of x, right? And we're given a graph of f. So be careful. If you're integrating f prime, and this is maybe a bit early and cruel, but if you're integrating f prime, right, you want to think about what was sitting there that when you took a derivative gave you f prime. It's f, isn't it? Right? So the antiderivative of f prime would just get you back to f, and then evaluate that from 1 to 3. And then plug in the 3 minus plugging in the 0. So plugging in the 3, minus plugging in the 1. And then they gave you a graph of f, so literally you're just looking at what f of 3 is. Look at the graph, right? So if you plug in 3, I'm gonna have to look at my answer key, you cannot see that. So when you plug in 3, it looks like you're at 6, right? That's what that point was there, boom, 3 comma 6. And so when you plugged in 3, you're at 6, minus, and when you plugged in 1, it looks like you were at 2. Right? So that was 2, and that's why this one, final answer would be 4. So watch out for that. And the last few is just making sure if we have a table, that we can also do the same thing here with the table. So the table above gives these values. If f prime is continuous, what is the value of the integral from -4 to -1? Again, there it is, that integral along a prime, right? So if you're integrating a rate, you have to integrate a rate to accumulate. So we're going to accumulate some values. Again, here, the antiderivative of f prime would just get you to f. Evaluated from -4 to -1. So plugging in the top thing minus plugging in the bottom thing. So f of -1 minus f of -4. And then if you check your chart, f of -1 was -1.5. Minus f of -4 was 0.75. And that's why final answer on that, we should end up with -2.25. Which I believe was letter B. So notice both this problem and the problem before, you were integrating along f prime, so that's how you ended up back at f. All right, and last little bit here is just, again, that the integral of a rate of change gives net change, right? So the integral of the rate of change of g, some g, from a to b is the change in g from a to b, right? G can be any function with a continuous rate of change, right? G prime can model lots of different rates of changes, such as, right, the rate at which a person makes friends in people per day, right? The rate at which children consume jelly beans in pounds per minute. The rate at which pollutants escape from a smokestack in tons per month, right? So we can have a lot of different references on that, right? So here's a real life example. I think we actually saw this in one of our Riemann sums or trapezoidal sums the other day. I remember a group drawing a very lovely picture of a tub of water, right? But they gave you this table, and they're telling you that these are the values of the temperature of the water at these certain times, right? It says use the data in the table to evaluate what the integral from 0 to 20 along w prime of t. Using correct units, interpret the meaning of this. So I want you to go and try that on your own. And here is the correct answer for this problem. So big idea again here, if you're integrating w prime, you'll get back to w, right? So the integral of w prime will get you back to w, evaluated from 0 to 20. Plugging in the 20 minus plugging in the 0 would get you, let's see, w of 20 I looked up there was 71, minus w of 0 was 55. So 71 minus 55 was 16. Right? So what did that mean, right? That means that 16 degrees Fahrenheit was the change in temperature from t equals 0 minutes to t equals 20 minutes, right? And this is this idea that you're looking over an interval, you'll be looking at how much that thing changed over that time. Okay. If you have a rough sketch, you know, if you have degrees Fahrenheit per minute times minutes here, when you go to integrate, the minutes would cancel out, right? And so you would just be left with the degrees Fahrenheit. All right, y'all, hope that made sense. Bye.